Welcome back to more trigonometry. If you've been with me for a while, you'll notice we've talked a lot about the law of sines. Today, we are going to see another interesting result connected to the law of sines. It is called the circumcenter. What is the circumcenter, you may ask? It is a point such that if I align my compass, all 3 points of the triangle lie on the circumference of this circle. So in this case, the circumcenter was about right there. Notice this is an obtuse triangle, meaning this angle is greater than 90 degrees. As we go on, I want you to think about what would happen if we were to find the circumcenter of an acute or a right triangle. To begin, we are going to start with a circle and work backwards, in a sense. First, some definitions. We call this the central angle because it emanates from the center of the circle to form this arc. This angle emanating from the circumference of the circle is called an inscribed angle. Central angle, inscribed angle, arc. Now I've drawn this in such a way that running a vertical line splits it into 2 equal isosceles triangles. If I define the entire inscribed angle to be theta, that means half of it is theta over 2. Because this is an isosceles triangle, up here is also theta over 2. Meaning this angle in the middle is equal to 180 degrees minus theta. Now if I extend the line all the way up, we know that there are 180 degrees in a line. So if this side is 180 minus theta, this side is theta. Now we said these 2 isosceles triangles are equal to each other by the way I've constructed it. So this length is equal to this length, meaning we effectively have another isosceles triangle if I draw the chord up here. So if this side is theta, the other side is theta, meaning altogether the central angle is 2 theta. So to summarize our reasoning, I've stated here if the inscribed angle is equal to theta, the central angle is equal to 2 theta. Now because theta was arbitrary, this applies to any inscribed angle and central angle in a circle. Let's build off this idea by constructing an arbitrary triangle inside of a circle. So here I've labeled it with side length A and angle A opposite. If I were to draw a central angle from the center of the circle, A being the inscribed angle, then 2A is the central angle. Following from our reasoning here, there might be a slight modification to deal with scalene triangles instead of isosceles. So I'll let you ponder that and come to your own conclusions. If I split the central angle into 2 halves, A on one side and A on the other side, notice I have formed 2 similar right triangles. This is going to help us out a lot. Of course, the radius of a circle being r and sine being opposite over hypotenuse means I have sine of angle A is equal to A over 2 over r. A being the full length, A over 2 being the half length. By rearranging, I get 2r is equal to A over sine of A. By definition, twice the radius is the diameter of a circle. So to connect it back to the law of sines, A over sine A is equal to B over sine B equal to C over sine C, which is equal to D, the diameter of the circumcenter. Remember how when we split this into 2 right triangles, it split the length of A in half. We call that a bisection. And because this is a right angle, it is a perpendicular bisector. So given an arbitrary triangle, to find the circumcenter, you simply find the intersection of the perpendicular bisectors, as I will next show. Before we get there, let me first demonstrate how to construct a perpendicular bisector using a compass and a straight edge. Given a line segment from here to here, I simply set my compass equal to that length. I run an arc from this point and another from this point. Notice there are two intersections, one at the top, one at the bottom. I connect my straight edge and draw a line. This here marks the midpoint of this line segment. Now I can measure with a ruler and verify that it's the same distance on each side, and I encourage you to try this for yourself at home. But also, extending a line upwards will be perpendicular to the original baseline. Keep that in mind should you ever need to construct a perpendicular bisector. In practice, that might actually be rather cumbersome. So for this example, I've simply measured the midpoint, and I'm going to use this perpendicular edge to make sure it bisects at a perpendicular angle. You know you've done a good job when all three lines cross at the same point. Sometimes, if you're a bit sloppy, two of them will match up and the third one will be somewhere else. That's a sign you might need to go back and take a little more care in your drawing. From the results we've just obtained, this is my circumcenter. So I will attach my compass from the center to the vertex, make sure it matches each one, and then proceed to draw the circle. Another check for how well you've drawn your diagram is that the circle will in fact touch each vertex on the exact point. So that's about all I have on the circumcenter for today. To revisit the question asked earlier, notice how the circumcenter for an obtuse triangle lies outside the triangle, whereas the circumcenter for an acute triangle lies on the inside. Where do you think the circumcenter for a right triangle would lie? Let me know in the comments section below. If you enjoyed this video, please like it and subscribe to my channel to get more videos like this in the future. Thanks for watching. I look forward to seeing you next time.